So thank you, Arvin. Thank you to the organizers for asking me to make a presentation. I'm going to kind of distill some of the elements that were presented in the previous talks and look at a specific application here to modeling the magnitude 7.1 Ridgecrest earthquake. And I do want to acknowledge Arvin's participation in this study as a co-author. So the objectives of this work, we're going to examine the adequacy of the Graves and Pitarka 2016, GP 2016 hereafter, kinematic rupture generator to model the near fault ground motions for the magnitude 7.1 Mainshock. And one of the main parts of this objective is to explore the upper frequency limit, the deterministic modeling aspect of this when we use this GP 2016 approach. Additionally, we want to investigate the impact of the proposed change in shape of the shallow slip rate function on the ground motion levels. And this is something that Arvin had mentioned in his previous talk. This is guided by the dynamic ruptures. The approach we're taking here is to run 3D broadband deterministic simulations. This will be up to about 4 Hertz for a suite of randomly generated ruptures using the GP 2016 method. Now, keep in mind, we're using forward simulations to test the predictive power of the GP 2016 method. So this is not an inversion. We're basically trying to apply the method as we would for a future scenario type earthquake. But it is, in a sense, a validation of the methodology within that framework. We do need a geologic model, so we're using the SCEC community velocity model, SI. We've tied this into the near surface material based on VS30. In terms of quantifying the misfits, we're using a spectral acceleration goodness of fit metric, which has been designed primarily for engineering applications, but it fits well with this kind of an approach. In addition to that, the 3-component waveforms from the lowest misfit model are visually compared to the observations kind of as a ground truth check. Okay, so let's take a close look at the specifics. The magnitude 7.1 rupture, Ridgecrest rupture, occurred in kind of central part of California along multiple subparallel faults. They were striking northwest to southeast. The green traces here are the mapped surface displacements that occurred during the earthquake. The blue star here is the epicenter, predominantly right lateral strike slip mechanism, as seen by the beach ball. The Mainshock was preceded by a magnitude 6.5 foreshock about 34 hours before the Mainshock occurred, and that actually occurred on a set of conjugate faults, as indicated by these green lines. The entire sequence was fortunately well recorded by the Southern California Seismic Network. There are about 16 strong motion sites within 30 kilometers of the rupture. Those are indicated by the red triangles on this plot. The map here, the colors on the map kind of indicate the near surface geology as characterized by VS30. We use the values from Wills et al. 2015. So these values range from about 230 at the low end, that's the very light colors as indicated here in the valleys, and then go up to about 710 in the darker colors. Most of the recording sites are in VS30 of 350 meters per second or larger, so relatively stiff in a sense. Also, just to note, just west of the epicenter is the Indian Wells Valley. This is a sediment-filled basin extending down to about 2 or 3 kilometers in depth. And then there's generally harder rock and mountainous regions to the east of the rupture. Also to note, just off the northwest end of the fault is the coastal volcanic region. Okay, I mentioned about the spectral acceleration goodness of fit. So this is one way of comparing models and observations. To start with, just to get an idea of kind of the general characteristics, I want to do a comparison of the observations with ground motion prediction equations. So the process of doing that is we start with the recordings. Here's an example for one site, the two horizontal components of motion. And from those two horizontal components of motion, we compute the spectral acceleration, and we're using the ROT-D50 parameter. So that combines those two horizontals into a single metric. And that's shown in the plot on the right. So we're looking at peak spectral acceleration on the vertical axis as a function of period. And that's can then be compared, in this case, with a ground motion prediction equation. So as an example here, I'm using the ground motion prediction equation from Abrahamson, Silva, and Kamai, 2014, from the NGA West 2 project. That's shown by the red curve. And we're using the site-specific parameters for this particular location. In this case, visually comparing these two, the match is pretty good. To quantify that, we compute residuals. So we take the difference of those two curves, we plot them out as a function of period, and that gives us the curve on the lower left. We then apply that same procedure to all of the stations. So these curves that are being plotted here are for the remainder of the stations. Now we have the 16 near fault stations. We can then take the, compute the average residual at each period, and that gives us the model bias. That's shown by the red curve here. And then and additionally, we can compute the standard deviation across these 16 sites. So the plot on the lower right is now showing how the model bias, shown by the red curve is the same in both plots, and the standard deviation for this particular ground motion prediction equation. We can apply that to other models, in this case, 3 additional NGA West 2 models, and now those are all plotted on the same curve. We can additionally average across the models to get a better idea of what the average, or how the average response model. Now there's some key features that we can pull out from these ground motion prediction equations. And the first is that out here at 5 to 6 second period, there's roughly 20% under prediction. So the 0 line, we're above the 0 line, that's under prediction. But also note there's a large variation, in particular the variation of the median prediction of these ground motion models. And that's because there's fewer data out there at those longer periods. As we move to shorter periods, we see that the curve now goes negative. The average curve is negative, so 30 to 40% under prediction from about 1 to 4 second period. Also note that the curves are much tighter here, closer, and that's because there's more data that go into the development of these models. So in the kinematic modeling, it's these features, and in particular this over prediction at 1 to 4 seconds, that we want to see if we can get a better understanding and maybe an improvement of that. Okay, so moving to the ground motion simulations, we're going to simulate the motions at these 16 sites. As I mentioned, we're using the SCEC community velocity model. The model is discretized at 20-meter grid spacing. We use a minimum shear velocity of 400 meters per second, so we're able to calculate reliable results up to about 4 hertz. In terms of the fault model, we use a 3-segment model as indicated by these black lines on the plot, is with a slight jog in this middle segment. That's based on the work of G et al. In 2019. Looking at a little bit more in terms of the seismic velocity structure, some of you may be familiar with the community velocity models from SCEC. There's some alternatives. So there's the SI model, and there's also the H model. We examine both, and just to kind of illustrate the differences, I'm plotting a cross-section along this AA prime profile. This is showing shear velocity as a function of depth. SI is on the top, H is on the bottom. In particular, you'll notice that in the SI model, this low velocity section here, just west of the fault zone, that's the Indian Wells Valley, and it's much a stronger representation in the SI model. That model has better in this region. These are both tomographically updated. There's more events and more stations that are used in the inversion for SI. And in addition, that model is consistent with previous refraction and structural geology studies. So that's the one we chose to do or to use here. Excuse me. Okay, now how do we parameterize the source? As I mentioned, we're using a 3-segment fault model. The total fault length is 52 kilometers and the width is 14 kilometers. So we've generated a suite of 5 randomized ruptures using the GP 2016 approach. Those ruptures are shown here on the right. These plots slip as a function of location on the fault for the 3 segments, as shown in the colors. Excuse me. You'll notice that there's quite a bit of variability among the fault models in terms of the slip distribution. That's a characteristic of the GP 2016 approach. We use an average rupture speed of about 60% of the local shear wave velocity. That's consistent with rupture model inversions. That's rather low, but that's a key feature of this model. The black lines are rupture time contours shown as the rupture propagates across the fault. Now, in this GP 2016 approach, there's depth-dependent effects of rise time lengthening, rupture speed reduction, as Arben had alluded to. And these are designed to mimic effects of velocity strengthening in the upper 5 kilometers of the rupture. Now, for each of those rupture models, we're going to run 2 realizations, and they use different slip rate formulations. So the one set is using the standard, what I call the standard GP slip rate, and that's plotted here. Arben had shown some of these, and Martin had also shown some representative examples. So there's a very strong or quick rise to a strong peak in the front, and then this long tail. In the standard approach, this shape is applied everywhere on the fault. Now the rise time varies spatially across the fault. It's partially correlated with slip, but the shape is the same. In the modified approach, modified GP, we're now implementing a variation of this shape in the upper 3 kilometers of the fault. So below 3 kilometers, it's the standard. From 1 to 3 kilometers, there's a transition as this slip rate function becomes more symmetric, and then it's in the shallow part becomes entirely symmetric above 1 kilometer. And this is guided by the dynamic rupture modeling, velocity strengthening strongly in that upper part of the fault. So we want to compare the impact of these 2 different formulations. Now, just from looking at this plot, you can see that this modified approach is going to shift the energy release to lower frequencies in the upper part of the fault. What I'm showing now is just an example of one simulation, just to show some of the waveform effects. You can see as the fault ruptures bilaterally, there's strong rupture directivity off the ends of the fault to the northwest and also to the southeast. The white triangles here are locations of the recording sites. Notice also in this model that you do get some channeling and focusing of energy off to the west, and that's the effect of that 3D basin. Looking at some specific sites, here's a comparison of recorded in black and simulated in red ground velocity waveforms. This is a site off the northwest end of the fault. Here, visually, there's a very good correspondence between the simulation and observations, both in terms of the shape and the frequency content of the motions. Moving to a site very close to the epicenter, CLC, this site, we actually produce a very strong pulse at the initial part of the rupture. This is a directivity pulse, and we don't see that in the observations. And I suspect what's happening here is that the actual rupture was very slow in the initial part, very kind of fragmented, broke up the coherency. And that's for this particular site, that's something that we're missing. Looking at a site here now off to the west in the basin, in the beginning part, we're not doing too bad, but you'll notice that the observations have these large amplitude late arriving phases. These are basin generated surface waves. And unfortunately, even though the model has a basin, it's just not sharp enough or strong enough. So this is indicating an area that needs improvement in terms of the geologic characterization. It's not in the source, but it's in the geologic structure. And then at the very south end, CCC is another site where in the beginning portion, we're matching pretty well, but then there's this late pulse of motion. This is most likely a very late sub-event in the rupture. The inversions show this. We just did not happen to capture this in our particular suite or in this particular rupture that I'm showing here. Okay, so just looking in a little bit more detail of how we quantify the goodness of fit, we're going to apply the same procedure as was done with the GMPE. So just to refresh your memory, here's the GMPE result that I showed earlier. This is the result that we get for the standard GP method. So each of the 5 realizations with the standard GP slip rate is shown by the gray curves here. And then the average across those are indicated with the red curve. So the average bias and then the standard deviation. And one thing you'll notice is that with a standard approach, we actually get a response that's very similar to what we get with the GMPEs. So we have the same level of overprediction, kind of large variability across the models here. Underprediction here at 5 to 6 second period, and then about 30 to 40% overprediction, primarily between 1 and 4 second period. Moving to the modified approach, so now we've just changed the shape of the slip rate function in the upper part of the fault. Slip distributions are all the same, and this is the response that we generate with those rupture models. And it's encouraging that just by changing the shape of the slip rate function, we improve the fit in these mid-period ranges from about 1 to 4 seconds. We're closer to this 0 line, still a little bit over predicting, but and that has to do with the details of the particular rupture. But this is a very encouraging result, and it suggests that this is an effect or a feature that we probably need to account for, particularly when we have ruptures like Ridgecrest, where the fault, as it comes up to the surface, is very complex, multiple subparallel segments, probably breaking up new rock or breaking through new rock. So a lot of the energy of the rupture is being consumed doing that as opposed to going into ground motions. And that's what's changing the shape of the slip rate function, and that's reflected in the ground motions. Just to look at a couple of other metrics, this is showing the horizontal displacements. And we're looking at just one particular case. This is the lowest misfit case. These sites are the 8 closest sites to the rupture. And for each site, I'm showing the 2 horizontal components. I've integrated the recorded ground motions up to displacement, preserving the static offset using the technique of Bohr. The red are showing the simulations, black are the observations. And you can see that we're actually matching the displacements, the final static displacements, even at these basin sites, rather nicely. The one site we underpredict a little bit here is this near fault site, CLC. So this is a case where we're still not matching the details, but overall, pretty good. Now, the rupture in this case is shown here on the right. It has the largest slip, the kind of these largest slip asperity.
Rob, the time is up, so if you can wrap up, that would be great.
Yeah, okay. So, and this is similar to what we see in the rupture model inversions. So I'll just kind of quickly show the results here. The main takeaways, this change in the shape of the slip rate function is very important. And this whole approach demonstrates the ability of the rupture generator to produce these high frequency ground motions, boosting the confidence in this approach. And I will end there. Thank you very much.
Thank you, Rob.